Hello, good morning and welcome to this instance of the Gardener review meeting for the release 1.143 of Gardener. Today we have 5 topics on our list. The first 2 topics are presented by Axel and are about automatic MTU configuration for VPN and dual stack IPv4 and 6 networking support on the OpenStack provider. Then Theodora will talk about the Garden Shoot Trust configuration. Oliver will give us information about HTTP2 connection coalescing fix for Gardener Observability. And Nick will talk about gap 36 with the self-hosted shoot control plane exposure. And with that, I would say, Axel, over to you with the first 2 topics.
Yeah, hello, good morning. I'll start by sharing my screen. I guess you can see it. So the first topic is the automatic MTU configuration for OpenVPN. Actually, in our VPN configuration between shoot and seed, we always use the OpenVPN default, that is 1500 byte in the tunnel, and for OpenStack, or now also for other providers, we have larger MTUs in the network, in the shoot and seed network, and even the backbone between shoot and seed support this large jumbo frames. So with this small MTU in the VPN, we had unnecessary packet fragmentation and a lower throughput, actually wasted capacity that is actually supported. And we've seen a big problem when we had a large spatial distance between shoot and seed with a long, high latency of the packets. Then this small MTU really was hurting us. Yeah, the solution for the VPN, we introduced a new environment variable, OpenVPN out to MTU true, and we set it for the VPN seed and VPN client, the server and the client. Yes. Yeah, we implemented an automatic detection. So in the VPN container, we look at the default route at the container interface, inside the container, and just subtract the overhead for the tunnel, which is an IPv6 header for the HA VPN, the TCP header, and the OpenVPN overhead. For the non-HA case, it's actually simpler. In this case, the OpenVPN server can push this MTU to the clients, and we wouldn't have to configure anything on the client side. However, in our HA case, we have those bonding devices and the IPv6 tunnel device. So in this case, we explicitly need to adapt or reset the MTU to the higher value, or to the detected value. Yeah, we needed 2 PRs actually. This is the first PR is in the VPN repository to add this automatic detection, and the second is in the Gardener repository. Here we decided to opt in to this automatic detection via an annotation. Yeah, you just annotate the shoot, and the environment variables are propagated to the containers. So in the HA case, we have even 5 containers, the server, the seed server, the clients in the API server, and the VPN shoot. In both cases, the init and the main containers. Yeah, as we had really a case that was hurting us, we decided to cherry pick this feature to the release branches. As it's backward compatible, it shouldn't hurt as long as it's not the annotation is not set. Yeah, as a demo, I actually created 2 shoots. Actually, a reconciliation is enough, but it takes quite some time to roll all the API server pods, the VPN pod, the server VPN, and the shoot VPN pods. So I just created 2 shoots. This is now the first shoot. Just look at one node where an VPN pod is running. I just open a node shell and I look for an OpenStack process. Get the grep. And with the PID, I can look at the pod's network namespace. And look at the network interfaces. Here we see that our main interface has the large MTU, but the tap devices of the 2, yeah, this is the HA case. So the tap devices of the 2 VPN tunnels are the small MTU, the bonding device has a small MTU. So in this case, we would have a lot of fragmentation. So let's switch to the other shoot and do the same thing again. Let's enter to the process namespace and just look at the interfaces. And now the tap devices have the large MTU, the bonding device has a large MTU, and the tunnel devices also. These ones are a little bit too small. We need to adjust it a bit. But in general, this already gives us a good improvement with a large spatial distance between shoot and seed. As an example, with a shoot in Europe and a seed in Europe and a shoot in Asia, we have an improvement of 2 times to 3 times the throughput compared to the small MTU. I think that's already what I wanted to show for this first topic. Are there any questions to this one? If not, I can continue with my second topic. This is about IPv6 dual stack for OpenStack shoots. yeah, we have already dual stack for AWS and GCP provider extensions, and this PR adds the dual stack support now for OpenStack. It's not really complete as we don't have load balancer support in our OpenStack installation here. And so we just enable IPv6 for nodes, services, and pods, and for egress traffic. But you can't currently create an IPv6 load balancer service. It's enabled the same way as for AWS and GCP. You just configure your IP families with IPv4, IPv6. IPv6 only is not supported in this case. Then we added a new API field to the provider config of OpenStack. So you have now this IPv6. And here you have actually the choice between configuring a subnet pool ID, where you can allocate IPv6 addresses or CIDR ranges from, or you can explicitly configure node CIDR, pod CIDR, and service CIDR. Yeah, these options are mutually exclusive. If both are set, explicit CIDRs win. Yeah, what gets created in OpenStack? We create 3 new IPv6 subnets. One for the nodes. Here we have this Slack address allocation mode. And we also create subnets for pods and services. Those subnets are actually only created to allocate IPv6 addresses. They are not connected to any router and not used for routing. We just give the CIDRs back to the Kube API server configuration and the Kube controller. Yeah, how do the nodes or the servers get the IPv6 addresses? They are simply attached to the IPv6 subnets, and then they will get assigned an IPv6 address. For that purpose, we also had to change the API for the machine controller manager for provider OpenStack. Now we have this subnet IDs field here, which is an array, and you can provide an IPv4 and an IPv6 subnet ID. For pods and services, yeah, we allocate the CIDRs via the subnet pool or via the explicit configuration, and then give the CIDRs to the Kube controller manager, the Kube API server, and the CNI plugins. Load balancers are not yet supported. Yeah, the difference to AWS is actually in AWS you can attach an IPv6 address to the VPC and to existing subnets. In OpenStack we have this 3 new to create these 3 new subnets. And yeah, address assignment is also interesting. In AWS, we have DHCP for v6 addresses, and Slack and OpenStack, where the server, yeah, it's a stateless approach, and the server just tries to create its IPv6 address more or less randomly, and just checks if it's already used or not. That's it for that part, and I can show you actually the 2 shoots I created here are already IPv6, and So we have the nodes. Maybe we can look at one of them and check the addresses. Yeah, so in the nodes, we have now here in the pod sitters already the range for the IPv6 sitters, and the node itself has also an IPv6 address. If we look, maybe at the network problem detector pod. So we have an IPv6 host IP and an IPv6 pod IP. I can also show you some of the OpenStack resources. Just list the subnets and grep for my shoot. Yeah, now we have 4 subnets, one for IPv4, one for IPv6, yeah, one IPv4 nodes, one IPv6 nodes, and then we create these service and pod subnets to allocate the addresses. And maybe also the servers. No server. Server. Here we have now, we also see the IPv6 address here. Maybe something I need to mention here is that in our OpenStack installation for IPv6 egress, it's only working when we configure if we configure NAT for, where is it? The network config. Yeah, it's this configuration that is needed to have IPv6 egress. So we do a source NAT on the node, and then it can be correctly be routed back, as we don't have or I don't have access to the router for egress traffic to configure the pod ranges here correctly. But you have IPv6 egress. You just don't see the pod IPs from outside, just the node IPs. I think that's actually it also for this topic. Are there questions?
Thank you very much. If there are no questions, then I guess we can go to the next topic. Eudora, handing over to you.
Sharing my screen now. Okay, I want to present a new component that we have introduced called the Garden Shoot Dress Configurator. There is also a guide available at the public documentation about how you can enable trust between a shoot cluster and a garden cluster, and I will go over this guide now, but let me show you the target simplified architecture. We have the shoot cluster, we have the garden cluster, and in blue I have annotated some things that need to be configured, but let's start with the problem. We have some shoot clusters and their workloads, and some workloads need to communicate and authenticate to the garden cluster, and we need to derive their identity. We don't want to create some static credentials and distribute them to the shoot clusters. Ideally, we want to get their native identity, their service accounts, and use them to authenticate to the garden cluster. From the shoot perspective, we just need two annotations, the managed issuer and mark the shoot as being trusted. But from the garden perspective, apart from the garden shoot trust configurator, we need also the OIDC webhook authenticator and the discovery server. I will show you a sample scenario now. I will go back to this picture later, but I want to show you a sample scenario where we'll have the shoot cluster. It gets a token for its service account. It uses this token to authenticate to the garden cluster, and then the OIDC webhook authenticator will extract the identity of the workload, and it will provide it to the garden cluster. Then we perform some airbag checks or some authorization checks, and we return a response. Let's first show, I have already created a shoot that I have marked as not as trusted, as having managed issuer. This means that the discovery server, the discovery server can now present the OpenID configuration, the well-known endpoint. So let's just check it. We have the shoot in its namespace. We can get its issuer. The issuer is available under status. You can find it in the advertised addresses and service account issuer. This is the URL that we can call. The well-known. And we can see using this endpoint that we have the issuer as it was configured in the shoot. We also have the URL of the JSON web key set, which is used to validate the tokens and other useful information. And now that we have seen that the shoot has managed issuer, we can mark it as trusted, adding the other annotation that I showed. So trusted, I will copy the annotation. And what just happened now? We marked the shoot as trusted, which means the garden shoot trust configurator created an OpenID Connect custom resource for this specific shoot. I will show you the OIDC. It has a predefined name from the garden shoot trust configurator. And let's see it. So we have the OpenID Connect resource, which is managed by the garden shoot trust configurator. It has the name, which has the shoot's project, the shoot name, and the ID of the shoot. Also, we have defined the expected audiences of the tokens that we will be issuing, and some prefixes that I will explain later where we can see them. Also, we have defined that we extract the identity from the username claim of the token and the group's claim of the token. Let me create a token to show you how it looks like from the shoot. I'll create it for the default service account in the default namespace. Okay, and let's just see the token. We have the audience as we specified it, and it needs to match the OpenID Connect resource. We have the issuer that we have seen, and the identity of the service account, which is in the default namespace, the default service account. This is the subject claim, and we don't have a groups claim. This will be the format of the tokens that we generate when we provide some workloads which have projected service account tokens. I have already created a sample pod. Let me show you the manifest file for the pod. This pod, its main idea is to just query the garden cluster and get the shoots in a specified namespace. For example, to perform a health check, but this is just a sample example for the demo. And this is done in 3 seconds. So my goal now is to apply this pod to the shoot and see that this pod is authenticated. We have not provided any roles for this identity, so I expect that we will be unauthorized, but again, we will be authenticated. Okay. We can check the logs. And this was the expected scenario. We are now authenticated, but we are forbidden because this identity can't do anything in the garden cluster. That's why I have prepared an airbag to apply in the garden cluster. And now I expect that we are able to start seeing the shoots in our namespace. Let me show you the airbag that I applied. This is for the garden cluster. I created a cluster row because we need to get the shoots and a row binding for the subject, which is a user. And this user has a specified format. This format is also explained in the guide, but we use the prefix which was in the OIDC resource. This is the prefix, which is the namespace, the shoot name, and the shoot ID. And then we extract the subject claim, which is the default namespace and the service account that we provided in the demo pod. The demo pod has this service account, and we used the projected volume. So we can have a token which we will use to call the Gardener API server. So I'm going back to this diagram, and we saw that we created a pod which was able, using a projected service account token, to call the Gardener API server. The Gardener API server didn't recognize this token, so it just forwarded to the OIDC webhook authenticator, which does its magic and authenticates the token, derives the identity, and then returns the identity with the prefix, with the username and the groups. And then we did the checks of the airbag. So pretty much this was the demo. And To simplify this architecture for you, the discovery server is can be deployed using Gardener operator. It already is available there. And those two components, the Garden Shoot Trust Configurator and the OIDC Webhook Authenticator, are available on an extension, Shoot OIDC service. This extension has two extension types. The first one, it deploys the OIDC Webhook Authenticator in the Garden cluster, and also we have the Garden Shoot Trust Configurator in the Garden cluster. It can be deployed. We just need to enable it. This was pretty much the demo.
Thank you very much.
Any questions?
Seems
thank you.
that there are currently no questions. Thank you also for your presentation. And then let's hand over to Oliver for HTTP2 connection coalescing fix.
Hello, good morning. Yeah, another week, another PR I can present on behalf of someone else. This time Johannes is on vacation, and yeah, I'd like to present you here this fix he recently provided. You might remember that we moved away from Nginx recently, and yeah, replaced it by native Istio resources. And by doing that, we introduced yeah, a weird bug when you access our endpoints via browser, especially. And this happens because browsers wants to use connections or share connections as heavy as possible. Yeah, the issue is we have wildcard certificates for some of our endpoints, like the observability components. And so here, like starexample.com. And so one domain, Johannes mentioned, named it aexample.com, but and bexample.com, but it could be like Plutonu and Alert Manager. And when you access one of the domains with your browser and do all the authentication stuff, and this works, and then you try to access the second domain, you get a strange and unexpected 404 error. And this happens because your browser is trying to reuse this HTTP2 connection you recently created, and the browser identified the Istio used the SNI from the first connection to determine the routes, or the routes which it could select, and it continues with this first SNI. So yeah. It does not find a route for your second. Well, I'm hopefully able to show it in a demo in a second. That's easier to understand. Yeah, and there's a fix for it. Johannes created just another Lua filter, which sends an HTTP code, the 421 in this case, which is kind of made for this case, so that the browser creates a new connection when there's a mismatch between the requested server name and the authority header. Okay, let's see if it works in the demo. So I prepared a remote setup because you cannot reproduce it in the local setup. We don't know why maybe the load balancers behave differently than the ones in the real infrastructures. But yeah, I don't know. Let's see how it's looking like on a real infrastructure. So I'm using the garden domains, the virtual garden alert manager, and I prepare also the long-term Prometheus. And let's see how it looks like when the fix is not active. Okay. So I try to access the alert manager. Looks okay. So first, I need to get the secret to authenticate myself. And then I get the strange, did you mean whatever thing? And it works. So alert manager is working. Check. Then I try to access the second domain, the long-term, Prometheus long-term. And we have this wildcard certificate for the ingress.runtime garden and so on. Yeah. Okay, let me do it in a second. Tab, and you see here now there's an HTTP error 404. And this is kind of unexpected because the page should be there. And when you look at the Istio logs here in the screen, you see here first it starts with the alert manager lines. I accessed here my alert manager and so on. Everything works. 200, 200, 200, 200. And the last line, there was a root not found issue. And the strange thing here is that here the authority header differs from the requested host header. So here we see the alert manager. This comes from the first connection the browser created when I access the alert manager. And here it tries to access the Prometheus using the same connection. And this does not work because our alert manager endpoint has no route for the Prometheus long term. Yeah, and we can fix this, or we fixed this with this Lua filter. I just deleted it here. I do not deploy the last version and so on because it really takes too much time. Okay. So let's see if the envoy filter is back there. So here this is the fix Johannes provided, this envoy filter. And let's do this thing again. My alert manager connection here. Probably I have to it's already working. Okay, works as designed. I was thinking about whether I have to start a new session to get a new connection, but it fixed it already. So yeah, now I'm able to access and to refresh both pages. Yeah, and when we check the logs here, we see now that the alert manager and the Prometheus, that those two things always fit now, because because of this fix, which was sending the 4.2.0 status, the browser is enforced to create a new connection. And we have lines like this here for the Prometheus. You see 2 times Prometheus, and the same for the alert manager. Yeah, so this is now working by just introducing another Lua filter. Yeah, that's it. Any questions?
We don't see that the filter kicked in and changed something, or do we?
You see it in the middle.
No,
There's the
not in the
421
access
response.
logs.
Yes, you see it in the middle, the Lua response.
You see it?
421. If you search for 421, you can see it.
Here, yeah.
Okay.
We see it.
Yeah, got it. Thanks.
You have sharp eyes, Luca.
I have a question, because the fix basically is like, okay, we won't support it. Did you also investigate if we could, what we would need to do to support HTTP coalescing? Because from what it looks like, the problem is kind of the mixture that we have wildcard certificates and at the same time have a gateway for every virtual service, right? So you could either have dedicated certificates and the browsers wouldn't even attempt to coalesce the connections, or you would have one shared gateway for the wildcard certificate and then virtual services behind that. But I guess that would mean changing too much, and you just wanted to have a quick fix for now, or do you plan to change more at some point?
That's basically it. We wanted to have a fix for now, because otherwise, there are more changes, like creating more certificates, which might be the first best solution from my point of view. One shared gateway is probably hard to handle. When you add more endpoints, remove endpoints, and maintaining a one gateway resource, that would be hard to handle, from my point of view, in my opinion. Yes, the first best thing I think would be to create an own certificate for each endpoint. This would be easy here for the virtual garden case, because there are only a couple of endpoints. It might look differently when you look at the seed, because the same thing happens on the seed when you access the Plutonu of shoot 1 and then Plutonu of shoot 2, and both are hosted on the same seed. You have the same issue. And here we have much more certificates or DNS records we would have to create then. So we need to investigate to really support it and find a proper solution for it.
All right, thank you.
But at least it's working now, and you don't get strange errors when you try to access Plutonu or whatever.
Any other question for now? In that case, I would say thank you very much again, Oliver, for taking over the topic and presenting it. And with that, over to Nick and GEP36.
Yeah, thanks, Luca. I will just quickly share my screen. All right. Hope you can see it, but should be fine. Yeah, I will just start off by giving a quick recap on why we need GEP36, just so you are all in context here. Basically, the problem is that self-hosted shoots are not exposed through a seed istio ingress gateway because there is simply no seed. So this GEP tackles that problem and finds a solution for exposing the API server. And as you can see in this umbrella issue right here, you basically have a lot of PRs from the past that laid the groundwork, stuff like implementing the extension API. And I want to present two PRs today that basically build upon this groundwork. The first PR being support and provider local. So we basically add a controller and provider local that is able to reconcile the self-hosted shoot exposure resource. And the second PR being a change in Garden ADM init, where we basically wire everything in. So when Garden ADM init runs, at some point we have to decide whether or not the self-hosted shoot exposure resource should be deployed. And this is the case for shoots that have an exposure extension field set. So shoots have to basically opt into this. As you can see here, that exposure extension field, and only then the self-hosted shoot exposure custom resource is deployed into the cluster. And because I want to get a better overview, I have actually created a diagram here that will help you understand better what we did or what I did. And as you can see here, we are targeting the local setup, the managed infra case. GEP36 especially focuses on the managed infra case. For the unmanaged infra case, stuff like setting up the DNS record, the record that points to the control plane node endpoint must be done manually. But one thing to notice here is that the mechanisms like reusing the self-hosted shoot exposure CR can also be used or utilized in the unmanaged infra setup. But for this demo, I will focus on the managed infra setup. And as you can see here in the diagram, we have a part of the shoot spec right here. And this basically specifies the extension exposure field. And whenever this is set as part of Garden ADM, self-hosted shoot exposure custom resource will actually be created and deployed into the self-hosted shoot cluster. This is an important distinction right here. So we have the self-hosted shoot cluster on the left. On the right, we have the kind cluster, basically the bootstrap cluster. And whenever the self-hosted shoot exposure is deployed, we have an endpoints part right here that contains the endpoints of the control plane nodes. So we have one endpoint right here, this address, and this is contained in the spec. And after this custom resource has been created right here, we basically have a controller and provider local that is watching this resource and will then act upon changes. So the controller will then go forward and actually create two different objects in the kind cluster. They are created in the namespace of the control plane. So they are created in the shoot garden root namespace. And as you can see here, we have a service that is created and has type load balancer. So we want to expose this using the load balancer. And inside the kind cluster, we have the Cloud Controller Manager local running. And this will actually watch for services of type load balancer, then reconcile it, create the corresponding load balancer as a Docker container, and will then populate the IP in the status field here. And as we don't use selectors for this service, we create the endpoint slice ourselves. So the provider local will also create an endpoint slice, and this endpoint slice contains the address of the control plane node right here, and it will create an endpoint slice for IPv4 and would create a different one for IPv6. So for every IP family, an endpoint slice right here, and you can see that there's the label that matches it to the service. And after this has been created, Garden ADM init will actually have to go forward and update the DNS record. So the DNS record, after the cluster has been bootstrapped, still points to this address. And we now need to update it and restore it from the status that is right here. So after all of this has been created, the service has been created, the provider local will actually go forward and update the status here. And then we can use this ingress IP in our DNS record right here to point our record to the load balancer. And then in the local setup, as described here, you can just curl it and access it without doing stuff like port forwards and so on. So this simplifies the development flow a lot. And one thing I want to say before I show a local demo is that one of the next steps would be implementing logic in the Gardenlet, creating a controller in the Gardenlet. So right now there's the question on who watches the control plane nodes for relevant changes. What if there's a new control plane node or an IP changes? So this is not targeted by those two PRs, but there will be a follow-up PR that handles the logic or implements the logic in the Gardenlet. Yeah. And now I can jump into terminal session. And if I open the kind cluster, for example, or if I start by going to the self-hosted truth, sorry. In the self-hosted truth cluster, I have a self-hosted truth exposure resource. Maybe I need to make this a bit bigger. And as you can see, if I check what it includes, we have the endpoints right here. This is like one endpoint only. And based on this endpoint, the provider local actually went ahead and inside our kind cluster created a service that is named exposure root. This is in the namespace should garden root. And if I click on the service, then you will see that it has a status load balancer. And in here, we have the IP address of the load balancer. And what has also been created is an endpoint slice right here. We have the exposure root endpoint slice. And this has the IP address of the control plane node. And yeah, I now have this this service right here. And if I jump back into the self-hosted shoot cluster, I can then check the DNS records. And I see that I have a DNS record named root external with the domain name API root garden and so on. And this now has the correct value, so the correct IP of the load balancer that has been updated. And if I go back to the kind cluster, so where the initial DNS record is bootstrapped, and I view the DNS record inside of here, I can see this one has the old IP address, and this has been migrated to the self-hosted shoot and was then updated, or let's say restored. Yeah. This is basically everything I wanted to show. Any questions regarding the PRs?
I would like to ask a question.
Yeah. Sure.
So first of all, thank you for all of these efforts. I was wondering how does Garden ADM init determine for which provider type it has to create the exposure?
Basically, what we do is, maybe I can show. I have it open right here. Maybe a minute. In the init flow, in the init goal flow, we have this flow task right here, where it basically says deploying self-hosted shoot exposure. And inside of here, we just check if the extension exposure is set. And we then create, I can just hop in here. We then go ahead and inside the, when we deploy the self-hosted shoot inside of the code, we basically have some default stuff here, and we have a type for the self-hosted shoot exposure. And we will actually fall back to the extension type. So in our case, this would be provider local, but this could be any extension type that we want to use or have any extension there. We have some defaulting in place, but you can also specify this inside of the exposure field. So inside of the
exposure field of the shoot manifest then.
Yeah, exactly. Inside of the exposure field of the shoot manifest, you can set the extension. And this can include whatever you want.
All right, thank you very much.
Yeah.
Other questions? This does not seem to be the case currently. So thank you very much again, Nick, for presenting. And with that, we are also at the end of this meeting. Thanks for attending. Hope to see you again in 2 weeks for the next occurrence. And until then, have a nice day and rest of the week.
Thank you very much. Bye-bye.
Bye.
Bye-bye.